Electricity and magnetism. Starts with Coulomb's law, the electric force. Mr. P, the electric force that exists between 2 point charges.
F E equals Q over V.
The electric force that exists between 2 point charges.
Oh, K times Q1 times Q2 over R.
Okay, this is Coulomb's force, the electric force. K is Boltzmann's constant. Q1 and Q2 are the charges. Class R is not. It is. Fair enough. This is especially confusing because R sometimes is. Okay, so when you are taking the AP test, do you have to have the equations memorized? Yes, is the answer. For multiple choice, right? On the free response questions, you do get the equation sheet. You do not get the equation sheet on the multiple choice. Remember, you do get the table of information for the multiple choice, which has some useful information. You should make sure you're aware of what's on there. Clearly, you do. It's better to know the information that's on there and not have to look it up, but it is useful to still have that table of information. Let's see. The electric field. Oh yeah, so just in case you're curious, that means that by the, what is it? Is it a week from Friday?
Yeah.
By a week from Friday, you have to have all the mechanics equations memorized. Just throwing it out there.
All right.
So, the electric field equation, Sierra, general equation for the electric field.
Electric force over charge.
It is the force per unit charge. This is the general equation for the electric field. The electric field is defined, Bill, by what type of charge?
Small positive test charge.
Great, a small positive test charge. The dimensions on the electric field, Tyler, are?
Newtons per coulomb.
Or? There's an or. Who can give me the or? Eric. Volts per meter. We can have newtons per coulomb or volts per meter. This is the general equation. We can also have the electric field that exists around a point charge. Hamza.
KQ over R squared.
KQ over R squared. This is for a point charge. This means that we can figure out the electric field that exists around a continuous charge distribution. What equation are we going to use to figure out the electric field around a continuous charge distribution? Ms. Yang.
Integral of 1 over R squared, K times, well, K times EQ over R squared.
Basically, we're taking and we're splitting this continuous charge distribution into an infinitely large number of infinitesimally small charges dq. So dE is then equal to k times dq over r squared. The electric field then is equal to k, or the integral of k dq over r squared. Remind me, electric field lines. Just talk to me about electric field lines. Logan, tell me anything about electric field lines. How would you draw them? Where do they start? Where do they end? General rules about.
Positive to negative.
They go from positive to negative. True. Good. Okay. What else? There are other things we need to remember about how we draw electric field lines. Like we should know how they are always when we draw them off of a surface, for example. They're always perpendicular to the surface. And are electric field lines ever loops? John? Wait. Are electric field lines ever loops? No, they are never loops because they always start and end on a positive and end on a negative charge. So it's never going to be a loop, unlike a magnetic field line, which is always a loop. in order to work with, in order to figure out the electric field that exists around a continuous charge distribution, we need various types of charge densities. Please give me all three symbols. Mohit.
Electric charge density. There's the lambda.
There's the lambda.
Yeah, that's Q over L. There's the. How do I describe it? But I don't remember what it's called.
Good, describe it.
It's like the sideways P.
The sideways P thing. What's the name of the sideways P thing, Nitish?
A lowercase thing.
Lowercase sigma is equal to
Q over A.
Q over A.
And then the rho is Q over V.
Q over V. How do you spell rho, Meg? No. No, Jenkins? Nope. This is fun. Winter? R-H-O?
Is it R?
It's that silent
Lambda stands for, Emily, what type of density?
The linear charge density.
And?
Then the surface charge density.
And?
Volumetric charge.
Great. So we have the three different charge densities. Let's walk through a simple example because we have mostly forgotten how to do this particular item. So let's say we have a continuous charge distribution with a charge positive Q, which is a uniformly distributed throughout this rod with a length of L. And I want to know what is the electric field that exists at point P. Point P is a distance A from this continuous charge distribution. We are going to start with the equation the electric field is equal to the integral of K dq over R squared. First off, you should know the direction of the electric field at point P due to this positive uniform charge distribution. Class, please point in the direction of the electric field. Hi, Meg.
Right.
Ah. So now, what are we going to do next? Miller? We're looking for the electric field that exists at point P. We already know it's to the left.
We take the, we can bring out K because it's a constant. And then we know that lambda equals Q over L, which is also equal to dq over dx.
Notice, in the x direction, we have this little charge here, which is dq, and it has a width, dx. Good. So notice, rather than r, which is just a general equation for distance, we're going to use x because we're talking about in the x direction, and x is the distance to our little charge dq. Good. Tim, from here.
Using the lambda equation, we can say that dq equals lambda times dx.
Good. Keep going.
Then we can substitute the dq with the lambda dx. And since lambda is a constant, allow lambda to integrate with respect to x.
Okay. What are the limits on this integral? Match.
Is it a to a plus l?
X varies from a all the way to a plus l. Good. Take the integral, please, Sarah Jane.
It would be x to the negative 1 over negative 1. And then from a to a plus l.
Good. So we get negative k lambda. Let's do from a plus l. Oh, we have a negative, so we have a negative times a negative k lambda times a. Oh, let's see. Oh, goes to the negative 1 power. Duh. Oops. So, sorry. So we have positive, no, do it this way, k lambda over x from A to A plus L. This whole thing is negative. Bring it up here. The electric field then is equal to the negative of the quantity K lambda over A plus L minus K lambda over A. We'll just rearrange it. So K times lambda times 1 over A minus 1 over A plus L. K lambda times A plus L minus A over A times A plus L. A cancels out. We get K times lambda times L divided by A times A plus L. Just math. We're not going to leave it this way because we have lambda in there. What are we going to use instead? What are we going to replace this with? Nick?
AQ over L and then L's cancel.
I'll just do it this way. It's going to be the same thing, but if I rearrange this equation, we get Q is equal to lambda times L, and I can just replace lambda times L with Q. It's the same thing, just one fewer step. So the electric field then is equal to K times Q over A times A plus L. And we knew the direction, it's negative. This just gives us the magnitude. So we have the electric field. Just as a general review of how to do a problem of this sort, figure out the electric field that exists around a continuous charge distribution. Just a brief review. What happens if A is much, much greater than L? What happens to A plus L? A plus L becomes approximately what class? A. Therefore, we get the electric field would be equal to negative KQ over A squared times I, if A is much, much greater than L. Please describe for me why this makes sense, Eugene.
Can you repeat that?
Sure. Why does it make sense that the electric field would be equal to K magnitude be KQ over A squared if A is much, much greater than L?
Because as the R G increases significance of L.
The shape of it becomes less and less important and acts more and more like a point charge. When we get far enough away, it acts just like a point charge. We get the electric field that exists around a point charge. Good. Dorfstetter, that symbol is the symbol for what? The electric flux, the equation for electric flux, general equation for electric flux, not Gauss's law just yet, is, Bill?
The integral of electric field times dA.
I'm sorry, what kind of integral did you say?
The one with the circle.
Right, that's my point, is we're not to the one with the circle in it yet. Just the general equation for the electric flux is the integral of E dot dA, which you can get EA times the cosine of theta, assuming you have constant electric field area at theta. Which brings us to Gauss's law. Please tell me what Gauss's law is, Travis? I even gave you a hint, look.
The electric flux is equal to...
True. Week from Friday.
Yeah.
Okay, good. Sarah Jane.
The closed integral, surface integral of E dot dA.
Which is equal to what? So, charge inside what? Q in, charge inside, yes? Inside the Gaussian surface. Remember, when you're using Gauss's law, you have to absolutely, without a doubt, draw the Gaussian surface. Let's just walk through an example. Let's say we have an infinitely large sheet of positive charge. So this is a plane, not a wire. Goes out infinitely in all directions, but it's also infinitely thin. We know from experience that the electric field is going to have a shape that looks like this. We're going to use Gauss's law to figure out the electric field that exists everywhere around this uniform continuous charge distribution. So we start out with Gauss's law. What do we do next? Go ahead.
Draw the Gaussian surface.
We're going to draw the Gaussian surface. Now, we're going to draw our Gaussian surface such that what occurs, Jenkins, on the left?
E field is constant.
The electric field is constant on the Gaussian surface. Close, we'll talk about some of the specifics having to do with that in a moment. We can bring it out from underneath the integral. What about dot product? Cosine of theta. I'll just put theta for now, okay? So we need to worry about theta. So theta needs to be what angle? We have a couple of choices here. Vlad? Choices. Vlad? Or 0. We need a cosine of either 0 or 90 degrees. What's the shape in this particular case that we're going to use for our Gaussian surface? Sierra? A cylinder. We could have all sorts of different shapes. We're going to choose a cylinder in this particular case. A cylinder where I'm going to draw it where the two ends would look like this and this. This is our Gaussian surface. It is a cylinder. And this would be the end of the cylinder. And this would be the side of the cylinder. Okay, that being said, notice that what is the angle for the side? The angle for the side is, Sierra? 90 degrees. Notice that dA is going to be in this direction. The electric field is at a 90-degree angle to that. So for the cosine of 90 degrees is equal to 0. Therefore, we only need to worry about the ends here. So that means it's going to be the cosine of 0 degrees, because dA on the ends is going to be in the same direction as the electric field. Okay, then we have the electric field times the integral of dA in this particular case is going to be, Mr. P?
Just
The area of what?
area of this end. So would you multiply by 2?
Because it's going to actually technically be the area of both ends. So yes, we'll put 2 times the area of a single end. On the right-hand side, we have the charge on the inside divided by E naught. What are we going to substitute in for the charge on the inside here? Garrett?
I don't.
We'll see if Travis remembers. Travis,
Yep.
what you got?
Can you repeat the specific question?
We need to substitute something for the charge on the inside.
Can we go to the densities?
Oh, we are going to go to the densities. Which one?
The volumetric.
It's not going to be the volumetric because it's going to be the surface, because if you look, this is a thin surface, right? So we're just going to use the surface charge density. So we come over to surface charge density equals charge per unit area. Therefore, the charge on the inside equals the surface charge density times which area? Nick?
Area of
The area of a single end. So this is the surface charge area density multiplied by the area of a single end divided by E naught. Go ahead.
Quick question, is that a wire or a plate?
It's an infinite plane, is what they pointed out. It's an infinite plane sheet of paper. Well, this we'd have to do it differently if it were wire. Therefore, we get that the electric field is equal to the surface charge density divided by 2 times E naught. This is the electric field that exists. Now, notice that that electric field is not dependent on distance from the infinitely large plane because it's infinitely large. And if you recall, we used this to then figure out the electric field that exists between two of them, and eventually use that to figure out the capacitance that exists between a parallel plate capacitor. Let's do one other one. We're slowly running out of time, but I do want to make sure we do this one.
Like, looks like a clock.
Say again?
Everybody looked at the clock. Like,
Yeah.
really?
Yes, we are. I'm on page 1 of 4. We're running out of time. Don't worry, I'll move faster. All right, so we have a sphere of, it's a uniformly charged, a charged conductor. So if it's a charged conductor with positive charge, positive Q, where are all the charges, Hillary?
On the surface.
On the surface. And therefore, we know the electric field is going to be uniform and going to look like this. We're going to figure out the electric field. Oh, actually, we've already determined that the electric field on the inside is equal to, Meg?
The surface charge is equal to.
Ah, we have, but that was specifically for
Oh,
this
for the
specific
cylinder?
geometry. This is entirely different.
Oh, is that 0?
It is equal to 0. How are we going to prove that the electric field that exists inside this this conductor in electrostatic equilibrium is 0, 0? Two things. One, you should be able to say, we know it's in electrostatic equilibrium, therefore the electric field is equal to 0, but you should also be able to prove it. So one, you should know that, and if they don't ask you to prove it, you shouldn't prove it, you should just state it. But we also should be able to prove it. How are we going to prove that the electric field on the inside is equal to 0, James?
If you draw a Gaussian surface inside there, the cube then equals 0.
If we draw our Gaussian surface that looks just like this, we then have our electric flux is equal to closed surface integral of E dot dA equal to charge on the inside divided by E naught. As you said, the charge on the inside is equal to 0. Therefore, the only way for this to work is if the electric field is also equal to 0. Great. We're now going to figure out the electric field that exists outside where R is greater than the radius. So we're going to draw our second Gaussian surface. So that's our first one. Our second Gaussian surface, we're going to draw where it is out like this. And we then have, once again, Gauss's law. And we can do the exact same thing we did before. We know the electric field is constant, so we can pull that out from the integral. We have the cosine of theta. In this particular case, the angle between dA and the electric field is always 0 degrees. So this is equal to charge on the inside divided by E naught. Therefore, we have E times the area of the Gaussian surface, just to specify here, is equal to the charge on the inside divided by E naught. So the electric field then is equal to the charge on the inside divided by the area of the Gaussian surface times E naught. What is the area? Michael, how you doing? If you get tired, don't worry. We have lab tables where you can stand. The area of the Gaussian surface then, Dorfstetter, is?
What?
The area of the Gaussian surface. What's the equation for that? That would be the area of a circle. The shape looks like a circle on the board, but it is not. It's a sphere, therefore. 4/3 something. 4/3 pi r cubed is the volume of a sphere. Okay, so let's just pretend, for example, that you need to know this on the AP test. Just throwing it out there. And, for example, you flip out and you can't remember whether it's 4/3 pi r squared or 4 pi r cubed, but what is it? Where do you look? On the table of information, it tells you, Jenkins, that the area of a sphere is?
4 pi r squared.
4 pi r squared, okay? So, on the idea that that is possible to happen, just realize it's there for you. So we have the charge on the inside divided by 4 pi r squared E naught. 4 pi E naught, or 1 over 4 pi E naught, excuse me, we know is equal to Boltzmann's constant. Therefore, the electric field equals K times the charge on the inside, which I'm going to just call positive Q, divided by R squared. When you look at that? We already knew the answer, did we not?
Yeah.
Okay. Again, this is something you should have memorized, and you should be able to derive it. But in the idea that they don't always ask you to derive it, you should be able to say it acts like a point charge. Therefore, that is the equation.